2 to the x into your calculator, this one. Your equations for exponential functions, we're going to talk about transformations in a second here, but they're in the form y equals a. Remember, a talks about your vertical stretch and your reflection. And then we put a c in here randomly. No, we don't want to put a c. I will put. They put an inform one here. A b. All right. Let's call this a m base. I don't know what we want to call it. We'll call it a 2. And then we go b to the x minus c plus d. I put a 2 in there because the key thing when you compare graphs is they have to have the same base so that they're growing at the same rate. And then we're just moving it one way or the other, right? Up or down, stretching it. Okay? This 2 here, I put in because there's a 2 here. It could be a 3, then that'd be a 3, it'd be 4, it'd be a 4. The key thing is that your base has to be the same in order to compare them. Okay? Y equals 2 to the x in your calculator, I told you to type it in. That is a exponential growth function because it's growing, right? It's getting bigger fast. Do you see that? Like it starts off kind of slow and then whoosh, shoots up. So what that is that's a doubling function because the base is 2. Everything doubles each time. So if it was per year, if I had 2 in the first year, I would have 4 in the next year, then I would have 8, then I would have 16, 32, 64, 128, so it would grow really fast, right? At the beginning, it seems like it's growing slowly, then all of a sudden, whoosh, you're flying up, okay? So if I put in negative 3 into the y equals 2 to the x, I would get 2 to the negative 3, which is actually 1/8. Why? What do you do if you have a negative exponent? Yeah, you can move it to the denominator. If it's in the denominator, you can move it to the numerator, and it makes it, what? Positive. So this 2 to the negative 3, I could write over as 1 is 2 to the 3, which is 1/8. Correct? So whenever you have any number to a negative exponent, you actually have a fraction. This one would be base 2 to the negative 2, which is the same as 1 over 2 squared, which is the same as a quarter. This would be 2 to the negative 1, which is 1 over 2 to the 1, which is a half. What's anything to the power of 0? 0 is 1. There I'd get 2 to the 1, which is 2. 2 to the 2, which is 4. 2 to the 3, which is 8. And then 2 to the 4, which is 16. So at first, when it doubles, it doesn't seem like it's growing really fast. But if at 1 you're at 2, 2 you're at 4, 3 you're at 8, 4 you're at 16, 5 you're at 32, 64, it's going to grow fast, right? And how do we know that? Because our y scale is going to have to take into account that it's going to grow quickly. You can't just go 1 to 10 like a linear function would just keep going up by 2, up by 2, up by 2, and it grows nice and slow, right? Same rate. So I need up to 16. So I'm going to make my y scale be 2 and my x scale be 1. And often our x scale can say 1, but with exponential growth or decay functions, your y scale is going to have to get larger because it's going to grow quickly, right? Or you're going to have very few points on your graph. So we have negative 3 and 1/8. So very close to the x-axis. Negative 2 1/4. Negative 1 1/2. 0 and 1. 1 and 2. 2 and 4. Oops, forgetting that this, I just made my y scale be 2. Scary. Y scale is 2. So really, really close. 2 and 4. 3 and 8. Don't know how that just drew a dot in the line, but thanks, computer. And then 4 and 16. So the key thing when you change your y scale to something more than 1, highlight it with a highlighter. You don't have to highlight the x scale, but highlight it so then your brain keeps thinking, wow, you changed this, because I didn't. I did it, and then I didn't do it right away. You watch yourself. Okay, so what's going to happen with exponential functions, if they are not transformed up or down, is that they will get closer and closer to the x-axis but not touch it. So actually, as it gets closer and closer and closer, it's going to get closer and closer to 0, but it's never going to touch it. So it's going to run right along this x-axis, and then it's going to grow quite quickly. And remember, my arrow can only go a little bit above the last dot. You can't just send it, because you need accurate points, right? Your graph will be perfectly accurate, and then you guys just throw some random arrow at the end that's long, and then you lose points. Now, why is it running closer and closer and closer to this? Because exponential functions have a horizontal asymptote on the x-axis. What's the only thing that can move that asymptote? Think about it for transformations. What's the only thing that can move that? Vertical translation. Horizontal translations would just shift it, which would not move it. Stretches can't move it. Reflections wouldn't reflect it. The only thing that can move that off the x-axis is the vertical translation, right? So this is your horizontal asymptote. On the x-axis, what's the equation of the x-axis, guys? What's the equation of the x-axis? Y equals 0, because the only thing that is 0 on that x-axis are all the y's, correct? And the equation of the y-axis is actually x equals 0. Make sure you're writing this down. Okay, let's talk about the domain of this exponential function. What's the domain? It goes like this. X and out of the reals, because there's x's that don't exist, right? It just goes out. So the domain is x such that x and out of the reals. Are any transformations going to change that? Do transformations change x's and out of the reals? No, so guess what? Sometimes they're going to give you a function on a test, or I'm going to give you a function on a test that has the domain of x and out of the reals. And then I'm going to tell you which doesn't change it. And I'm going to make it affect a whole bunch of x things. And you're going to be like, oh, it has a horizontal stretch. It has a horizontal translation. It's going to affect the domain because that affects the domain. Can anything affect the domain of XCR? No. So I tricked you, because I'll give you an XCR domain, and then I give you x changes, and you'll be like, there's changes, the x change. Well, no, it's XCR. It can't change. Make sense? All right. Range. Y such that y is what? Greater than 0. It can't be equal to, because at 0 is the asymptote. Can we equal an asymptote? An asymptote's where the graph can't be. So it's y is greater than 0. So round bracket 0 to infinity. What kind of asymptote do I have? Horizontal asymptote. Logs have vertical. And this one's at y equals 0. What about my x-intercepts? Do I have any? No? No x-intercepts. What's my y? Okay. So when they talk about B, they're talking about A is 1, B is 2. They're talking about this right here. Okay? Everyone's following along? Y1, 2 to the x. Y2, 3 to the x. Go. Press graph. Remember, they draw them in order. So they'll draw the 2 to the x first, then 3 to the x next. What happened? It grew faster. Why? Because instead of doubling, it's now what? Tripling. Okay. Put in Y3, put in 10 to the x. It grew faster, correct? Closer to the y-axis, yeah? Okay, did my x-intercepts change at all? No, they still don't exist. Did my y-intercept change? Look at it. Did my y-intercept change? No, because 2 to the 0 is 1. 3 to the 0 is 1. 10 to the 0 is 1. So I need transformations in order for that y-intercept to move, correct? Just increasing my b value, or doubling, tripling, or tenning. I don't know what that is, but we'll just make it grow faster, but it's not going to change my y-intercept. It's not going to change my asymptote, right? All right. So here it says, if b is greater than 0, you get the shape above. This is called an exponential That is not true. It's called an increasing exponential function. Or an exponential growth. Now, if the form I'm only looking at is y equals a b to the x, my a for this is just 1, correct? It'd be y equals 1 times 3 to the x. My value of a is 1. My value of b is 3. What's my y-intercept? 1. So it's 0 and 1. Because when I fill in 0, I'm going to get 3 to the 0, which is still 1. What's going to happen to this next one? What's my y-intercept? What's this one? 0 and 1, right? How do the different bases affect the function? The greater the b value, what happens? The more b is greater than 1. What's happening? Larger exponential growth. Closer to the y-axis. Why does it get closer to the y-axis faster the larger you get? Why is it get closer to the y-axis the larger b value you get? What is the graph doing? Growing faster. It's growing faster. So the faster it grows, the faster it's going to increase, the closer it's going to get to the y-axis, right? So for example, if I gave you this graph, which had the same scale as this graph, which one has a larger base? Which one has a larger b value? The second one is growing faster, correct? So if I was in the form y equals a b to the x, and this was graph 1, and this is graph 2, you'd say graph 1 has a smaller b value than graph 2. True? Or graph 2 is a bigger b value than graph 1, right? Because it's growing faster. We agree? Flip over. So we looked at b values greater than 1. Now we're going to look at b values between 0 and 1. Well, let's look at 5 first. I got a little ahead of myself. I want the y-intercept of these. So first one we'll do together. Y equals 2 to the 0. What does that equal? Why did I put 0 in for x? Because x equals 0 when it's a what? Yeah, when it's a y-intercept. When it's on the y-axis, x has to equal 0, right? So this y-intercept is 0, 1. This one is going to be y equals 3 times 2 to the 0. What's 2 to the 0? What's 3 times 1? 3. So does it matter what unit I'm in? If I ask you for a y-intercept, what are you going to do? Put 0 in for x every single time. And when I say x-intercept, you're going to put 0 in for y. It doesn't matter what math curriculum we're in. That should be what pops into our head instantly. Correct? This one is going to be 4 and 2 to 0, which is 4 times 1, which is 4. Let's think about it. What are these in transformations? Vertical stretches. What's my original's y-intercept? 0, 1. And what am I going to stretch them by? 3, 4, 5.25, hence why they're 0, 3, 0, 4, 0, 5.25. We could use transformations as well to get these. Do we agree? Because your vertical stretch is going to change your y-intercept. Because your mapping, for example, on this one is going to be xy becomes x comma 5.25y. Right? Okay, we're going to put 1/3 to the power of x in our calculator. If you don't have a fraction button, you have to put this in brackets. If you do have a fraction button, please keep using it or start using it because you haven't listened to me this whole time. You should be grateful you have a fraction button. You were blessed with a fraction button. So y equals 1/3 to the power of x. What's your graph doing this time? So instead of a growth, it's a starts with a D. Decay. Because now every single one of your values is being thirded. Thirding is a word. It is. They're being thirded. So they're going to get smaller, which means they're going to decay, correct? Like radioactivity, you hope that it is a exponential decay function and not an exponential growth, or you're in trouble. Okay? Bacteria is often an exponential growth function. Scary. It just gets bacteria. Okay. So let's look at our y values. Our y is 1/3 to the -3. Grade 10. All of this is grade 10. We do exponent laws in grade 10, and then they're very much not found in 11. All right. So if you have a full fraction to a negative, what could we do to make it positive? You flip the entire thing and it becomes positive. So we'd actually get 3/1 to the 3, which is 27. So that's why you're getting that 27 there. This one, you're going to get 1/3 to the -2, which is the same as 3/1 to the 2, which is 9. So we're starting off at a bigger number and getting smaller. Does it make sense? This is a decay function. That makes sense. Yes? It should be getting smaller as we're moving along in time. 1/3 to the -1 is the same as 3/1 to the 1, which is 3. 1/3 to the 0. What's anything to the power of 0? 1. 1/3 to the 1 is 1/3. 1/3 to the 2. What do you do when there's an exponent on the outside? See how these exponent laws come back? But we drop them off for like a year and a half. Distribute to both, correct? We did this in binomial theorem too, so we talked about this already. So we're going to get 1 squared over 3 squared, which is a 9th. Then 1/3 to the 3. We get 1 cubed to 3 cubed, which is 1/27. And then 1/3 to the 4 is super small, 1/81. It's just going to keep getting smaller and smaller and smaller and smaller and smaller. Will it ever get to 0? No, because we're going to have a what there? Horizontal. I'm going to make my y scale still be 2. I just won't put the 27 on it. All right. So I have negative 2 and 9. 2, 4, 6, 8, 9. Negative 1 and 3. 0 and 1. Then I'm at a third. 9. 81. It's going to get crazy close without touching it, right? So it's going to run along here. And it's going to increase a little. Remembering that I can't just run that arrow where I feel. Because you'll have like the perfect graph and then you guys just like shoot an arrow off. And then I'm like, I have to take off marks. Because you've lost your accuracy. So remember, if it increased faster, it got closer to the y-axis. Yes? If it decreases faster, what's going to happen? So let's, once you're done doing that, go into your y2. Which is bigger? Let's take 1/3 completely out because people get messed up with that. Let's take the third out. Put y equals 1/2 x into your y1. 1/2 x. And then press graph. So 1/2 x, 1 over 2 to the x. Then in your y2, I want you to put 1/4 x. Which one's bigger, a half or a quarter if you're making something? A half is bigger, right? Half a cup is bigger than a quarter cup? Yeah. So remember, it's going to draw them in order. So what's happening? Which one's actually closer? A quarter is actually closer. So the closer you are to 0, the closer it is to the y-axis. The closer you are to 1, the further it is from the y-axis. If you want to write that, you can. Closer to 0, closer to y-axis. Closer to here, closer, further from y-axis. Say you forget. It gives you a diploma question. Okay, everyone's paying attention? It gives you a diploma question like this. And then one like this. And it asks you for which one has a b value closer to, well, that is, why would I put a bracket around that? And it asks you for which b value is bigger. I know this one's bigger than this one, because this one's a half, that one's a quarter, correct? See, that falls right out of your head. Can you not go to your calculator and put in a half and a quarter like we just did and saw which one's closer to the y-axis? Can you not put in trial and error values? You absolutely can. I would know that when I typed it in, oh, a quarter was closer to my y-axis. So this one actually has, this one's b value is larger. We'll go graph 1, graph 2. So graph 1 b value is larger than graph 2. True? Can you run test values on your b values? Absolutely, if you forget. And this one's b value is greater because this would be a half and that would be a quarter. Correct? So graph 1 b values, what the heck? It's not fair. What's the domain of the above graph? Yeah. X and M of the reals. What's the range? Y such that? Y is? What's the only thing that can change that? What's the only thing that can move it off of 0? Yeah. The vertical translation is the only thing that can move it off of 0. What's the only thing that could make it end up being less than rather than greater? Reflection in the x-axis would change that inequality sign, right? Okay, we have a horizontal asymptote. y equals 0, and I have no x-intercepts. And a y-intercept. 0. So if your b value is between 0 and 1, you get the shape above. This is called a decreasing exponential function. Or a exponential decay function. This one I star because everyone forgets about it. All right. What type of transformation, which we're going to talk about transformations in a few seconds here, what type of transformation can get us to go from y equals 3 to the x to y equals 1/3 to the x? If you're stuck, could you type them in? Look at them? Sure, do that. Do you have the answer? Okay, type them in and look at them. What's happening? Reflection in the y-axis is what's happening. We can see it. We can visibly see it, correct? But how can we prove it, that it's a reflection? Okay, I told you that we have to have the same base. This number down here has to be the same in order to compare them. Well, they're not. First problem. Okay, I can only compare them if they're the same. Are they the same? No. Can I make them the same? How? Negative exponent. So if I do 1/3 to the negative 1, it actually is 3, correct? So 1/3, if I raise that to the negative 1, it's going to become 3/1. So flip to the negative 1 with an x, correct? Which is the same as 3 to the negative x. What happens when I have a negative in front of an x? Yeah. Reflection in the y-axis. That's how you actually prove that it is. Looking at 6, it says given the points -2, 16, -1, 4, 0, 1. What function of the form y equals c to the x can be used? Now we're going by 1 each time, so -2, -1, 0. It has to go down by 1 each time, right? X's. And we're going from 16 to 4 to 1. What's happening? Is it growing or decaying? 16 to 4 to 1. It's decaying. Okay, so we know that the b value has to be between 0 and 1. At the very least, it's decaying, correct? Some people will tell me it's 4 to the x. That doesn't work, that grows. Okay, so I know it's decaying, it has to be between 0 and 1. So what do you think is going to happen? It's going to be 1/4. So if you know it's going up by 4, going this way, it's going down by, it's being multiplied by 1/4, right? Or if you say, I'm going to divide by 4 to get to the next one, that's multiplying by 1/4, right? So our b values are by multiplication. So this one would be y equals 1/4 to the x. Then we're going to flip over. And then we're back to transformation. So, in order to transform exponential functions, they have to have the same base. That's what we discussed, right? Make sure no one's on the phone. So we have to have the same base. So we have y equals c to the x, and we have y equals a c. Whatever we label this has to be the same. If we label it c, smiley face, piglet, it doesn't really matter. But this base has to be the same number. And then we have our vertical stretch, reflection in the x-axis, reflection in the y-axis, horizontal translation, horizontal stretch of 1/b. and then vertical translation. So nothing changes. Same transformations we've done all year long. Correct? So first thing it says is describe how the graph of the second function compares to the graph of the first function and determine mapping notation. Before I start an exponential, I always have to make sure these are the same. Are they the same? Yes. The next thing I have to make sure is that 4 appears nowhere in my transformations. Because that's just the base of the function. The base of this function is it is, instead of like doubling, tripling, this one is multiplying by 4 each time. Or it's going to, 4 to the power of whatever each time, right? So it's growing by 4. 4 times the amount. Yes? So this one is, and so is this one. So the only thing that's going to appear in my transformations is this 2 and this 2. That 4 appears nowhere, right? You guys want it to be somewhere, it can't be. So what does this 2 in front do? Vertical, stretch, what? By a factor of 2. About the x-axis. Is there a horizontal stretch? No. Same rule applies as before, though. We have to make sure we have 1 in front of our x, which we do. Are there any reflections? Nope. What is there still? Horizontal translation. 2 units. What? When we go to our mapping, we get xy becomes x plus 2, comma 2y. I want you guys to do B. X over 5, how could I rewrite it? Instead of x over 5, yeah? 1/5 times x. So you guys try B, and then try example 2, which wants x and y intercepts. The x-intercepts you can get from your calculator if you so choose. You'll find something out about them. And the y-intercepts you can do algebraically. So I want the y-intercepts algebraically. We're going to rewrite this as y equals -2, 1 over 5, x minus 4. That's an x, even though it's a little one. Okay, so this 2 and this 2 stay, right? But don't appear anywhere in our words or in our mapping. Yes, they just have to be the same so that we have the same curve. Guys, if it was y equals 2 and it was y equals 2 to the x and it was y equals 4 to the x, you're not even starting with the same curve right off the bat. You're going to have to get a stretch that's going to have to fix it so that there's the same curve, correct? So that's why the bases have to be the same so you have that same curve happening. And then you can stretch it, reflect it, move it, like beep it, bop it. What's that thing?
Bop it.
Bop it, but there's more. Twist it, pull it. Isn't there more? Pass it. She's here. All right. So we have a horizontal stretch by a factor of what? By a factor of what? So I'll answer 1. 5. About the y-axis. We have a reflection in the what? Almost done. Reflection in the what? Reflection in the x-axis. And vertical translations. 4 units what? 4 units what? Okay, what did you find out about the x-intercepts of these graphs, all 4 of them? There are no x-intercepts. Remember, your horizontal asymptote sits on the line y equals 0, correct? What's the only thing that can move it off of there? What kind of translation? Vertical translation. What's the vertical translation on this one? 0. What about this one? 0. What about this one? What about this one? Did you know that the horizontal asymptote, write this down, is equal to what? The d value, or the vertical, what? Translation. Right? The horizontal asymptote is equal to the vertical translation, because if it's y equals 0, it's still there, right? If it's y equals 2, it's now up 2. If it's y equals negative 3, it's now down to y equals negative 3, right? This is very important and everyone forgets about it. So these all have horizontal asymptotes at y equals 0, which is on the x-axis, which means these all have no x-intercepts. This one, if I go f of 0, it equals 2 to the 0. So it equals 1. So this one's at 0, 1. It's at 0, 1 because there's no vertical stretch. This one, f of 0, is 2 times 10 to the 0. That's a 1. So it's 2 times 1, which is 2. 0, 2. Please be quiet. So the vertical, guys, the y-intercept is at 0, 1, correct? This one is vertically stretching it by a factor of 2, hence why it's 0, 2. Yes? This one's stretching it by nothing. That's a horizontal stretch. We agree? So it should end up being 0, 1. Let's see. F of 0 equals to 10 times 0. 10 times 0 is 0. What's 2 to the 0? 1. So it's still 0, 1. Which makes sense because it's a horizontal stretch that's multiplying by 0. 1/10 times 0 stays 0. And this will give me negative a half. 5 equals negative 1/2. 3/5 to the 0 is negative a half. We are not done. Do not pack up. We already did example 3 on the other page. Describe. Go. 4. We're kind of doing our homework embedded in our notes, so let's go. So this one, we're just going to discuss it. This is a what? A reflection in the y-axis, and this is a vertical translation 3 down, and we can compare them because they both were base 10. We agree? Okay, this one is a base 2, this one is a base what? Not 2. Stupid not 2. So we have to make it a base 2. How do we make it a base 2? Make it 2 to the what? 2 to the negative 1, which would multiply by 3x, so we get negative 3x. Now can I compare them? Yes. So I have a vertical stretch by a factor of 5 about the x-axis, a horizontal stretch by a factor of 1/3 about the y-axis, and then this silly thing gave me a reflection in the y-axis. This one is trickery, just so you know. Base 6, base not base 6. But it's also a negative. It gets real convoluted. So 1/6 is 6 to the negative 1 times the negative x. What happens to the negative times the negative? It gets out of our life. So we get 6 to the x plus 3. Oops, plus 3 down here. Base 6, base 6. Now we can compare. So it's a vertical stretch by a factor of 2 about the x-axis and a vertical translation 3 up, and there's no reflection to be found. This one we can rewrite as 1/2 x. So it's just a horizontal stretch by a factor of 2. Right? Remember the negations get rid of each other. This one, it just wants to know what's the asymptote. All we look at is the what? The d value. The vertical translation is the only thing that can move it. So it's this. There's homework on here. Remember I told you I'm bumping the homework till later. I don't really care. We did a lot of homework today. What do you think I'm going to make you do tonight? One of the reviews. The review I'm picking is polynomials. So I'll post the link again so you know which one it is. There's no harm.